Hello everyone, we are from Group 1. Today we are going to talk about computational analysis of structural stability and energetics of caffeine and naphthalene molecular crystals. Before we start, let me introduce my team members. My name is Nur Syafiqah binti Khairul Bashar, and then we have Emilia Aisyah binti Mat Zahir. After that, we have Nur Syahira Tiliana binti Kamsani, and the only male in this group is Muhammad Syami bin Muhammad Shatta.
First and foremost is the introduction of our project. This project investigates molecular crystal stability and energetic through computational analysis. Using Gaussian software, it examines molecular arrangement and their impact on energy and stability, providing insight for both theoretical understanding and practical material design in diverse fields such as electronics and nanotechnology.
Okay, the first part is let's talk about the caffeine structure. Caffeine is a chemical compound that has a unique shape made by joining two small parts called imidazole and pyrimidine rings. These parts fit together like puzzle pieces to form a flat, stable structure. Then, the properties. Caffeine molecules like to stack on top of each other, much like pancakes because their surfaces doesn't mix well with water. They are hydrophobic, means they are hates water. The distance between stacked molecules is about 3.4 Armstrong, which helps create stable layers. These stacks influence how caffeine dissolves in liquids and how the body absorbs it. If the molecules come too much, it dissolves less, affecting how it works in the body. Why stacking matters? Caffeine stacks in a way similar to DNA building blocks, pyramid bases, making it useful in scientific studies about how molecules interact in biological systems. The application is, it is widely used in medications, not just as stimulant but to study how weak forces hold molecules together. It helps researchers understand self-assembly, where molecules organize themselves into patterns, and non-covalent interactions, which are weak forces like those in DNA and proteins. The stability factors is caffeine is stable in dry environments, but things like water vapor or UV light can change its structure. This can affect how it behaves, whether in medications or storage. Now I'm going to talk about naphthalene. Naphthalene is simpler than caffeine because it's made of two connected benzene rings forming a flat, symmetrical shape. This structure is strong and stable to the way its electrons are spread evenly across the molecule. The properties of naphthalene is it is very stable because of its aromatic nature, which is a benzene ring in the molecular structure, which means its electrons are shared across the entire molecule, making it hard to break apart. However, it easily turns from solid to gas at room temperature, which is a process called sublimation, which can release harmful vapor in the air. The application is it's commonly used in industrial products like mothballs, dyes, resins, and plastic. It has potentials in medicine for creating drugs to fight infections, fungi, and even cancer. Lastly, we are going to talk about the stability factors. While naphthalene is stable in controlled settings, its gas emissions can irritate the lungs and are suspected to cause cancer with long-term exposure.
And now I will be talking about the step-by-steps on how to build naphthalene. From the builder's menu, find the ring structures menu, and inside the ring structure find the benzene, which is a hexagonal shape. And then click on the 3D canvas twice so that you add two benzene molecules. After that, in the builder menu, click on the modify bond, which is represented by the bond stretching image, and click on two nearby carbon atoms like in this picture, and select the bond type as none to remove the bonds. After you've removed those at least three carbon bonds, click on the delete atom button, which is represented by the X button, and click on the atoms to remove it. so that it becomes like this image. And then click on the modify button again to connect the two molecules together. And for the bond type, make sure to select the double bond with one delocalized bond. Once you've done that, you can right click or go to the edit menu and use the clean function to arrange the naphthalene molecule in a more reasonable arrangement. And now for the calculation part of the initial lattice energy and the optimization of naphthalene. First of all, to find the initial lattice energy, go to the Gaussian calculation setup and set the job type to energy. And then set the method to be Hartree-Fock, and the basis set is 631GD with charge 0 and spin singlet. And then once you've found this value, and then the file is completed, you can then find the optimization of naphthalene. So to do this, go to Gaussian calculation setup, set the job type as optimization, and set the method to DFT and B3LYP, and the basis set is 631GD with charge 0 and spin singlet. And now I will guide through the step-by-step on how to build Caffeine. So for Caffeine, go to the ring structures in the builder menu and select isoindene. This is represented by a hexagonal combined with a pentagonal shape. And then click on the 3D canvas to add the molecule. And then go to the elements table in the builder menu and select the nitrogen atom. Click on 4 carbon atoms to replace it with nitrogen atoms in this position. And then go to the builders menu again and select the elements table and go to oxygen and select the double bonded oxygen. Make sure it is the double bonded oxygen and click on 2 hydrogen atoms to replace it. So now it forms a double bond with a carbon. And then go to the elements table again and select carbon and make sure that you select the tetrahedral carbon. This is the carbon that that is bonded to 4 other hydrogen. So now click on 3 hydrogen atoms to replace it with the carbon with the methyl group, which is CH3. Once you've done that, you manage to build Caffeine. And now for the calculation part of the initial lattice energy and optimization of Caffeine. For the initial lattice energy of Caffeine, set the job type to energy and set the method to Hartree-Fock with basis set of 631GD. And then once the system has run the values and produced an output, you can then find the optimization of Caffeine. To do this, go to the Gaussian calculation setup and set the job type to optimization and set the method to DFT, B3LYP, and with basis set of 631GD.
Next, let us discuss about the naphthalene. After optimization, the energy of naphthalene decreased from negative 383.4687 H3 to negative 385.8644 H3. So this indicates that a more stable configurations with reductions of negative 2.3957 H3. So the optimized bond length with C double bond C at 1.4014 Armstrong and C single bond H at 2.1467 Armstrong. This reflects that a proper electronic distribution reaching the perfect symmetry and minimize structural strain consistent with its aromatic character. Other than that, the optimized dipole moment of 0.00001 dBi, reflecting that near perfect charge symmetry and stability. So the absence of imaginary frequencies confirms that the molecule is at a true local minimum on the potential energy surface. So the optimized PANA structure enhance the pi electron delocalizations, reducing the strain and also ensuring the stability. Next, let's just discuss about the caffeine molecule.
which underwent optimization, resulting in a significant reduction in electronic energy from negative 676.15491 to negative 680.37699 H3. So this indicates that a more stable conformations. So initially, the structure exhibit random bonds and lack symmetry, leading to a higher energy state. So after optimization, the molecule's geometry was refined with bond length and angles adjusted to the lower energy, ensuring that a more stable configurations. So the RMS gradient norm of 0.000066 H3 per Bohr confirmed that successful optimization, while the dipole moment of 3.83374 dBi suggested that some polarity in the structure. So this improvement demonstrates that the caffeine crystal is more stable and energetically favorable for post-optimization.
To conclude our project, that this study used computational technique to optimize molecular crystal structure, focusing on caffeine and naphthalene. It demonstrates how structural modification enhance stability, with caffeine showing reduced energy and improved bond accuracy, and naphthalene confirming stability to resonant properties. The finding validate computational method like DFT and HF for predicting stability and provide a basis for application in materials science and industrial processes.